you would have to let me know. But everything, all the info is here, and the Zoom lecture is sort of, the link for the Zoom lecture is there. The main thing is that if you haven't used before, we're using CampusWire for announcements, and we're also using Gradoscope for homework, returning the homework. And so the CampusWire is, so if you click this, you'd go there and you enter a code, and you can, you can enter your email and so on. The main, the main thing is to just sign up there as soon as possible, because that's where we're gonna post announcements, not on CCLE anymore. So if you don't do it, you're gonna miss on the announcements. The Gradoscope, again, you go there and use the code to sign in or join, register, and then you submit your homework problems. So there is a final exam. There's a midterm, the date will be announced, and a final exam. Both would be take home. And the final exam, let's say tentatively, is around Thursday or Tuesday, June 8th, which is the official date. The time would be flexible, so you'll have more than the amount that's sort of stated on the official register website. So there's going to be homework, usually weekly, and that would be 20% of the grade. The midterm is 30%, and the final is 50%. Prerequisites of the class are Stat 100B and linear algebra, such as Math 33A. But we rely heavily on linear algebra, so any exposure, any background there is useful. Homework, slides, and notes will be posted on this box folder here. And I'm gonna also post lectures. So currently not, the current lectures are, there's gonna be a playlist there once we have lectures. There are sort of previously recorded lectures from just the last quarter and last year. And so what I'm gonna do, which I tried last quarter, is to ask you guys to go over some of these recorded lectures from the spring 2020. Those are the complete lectures before coming to class, and then we try to discuss and get people involved in the discussion, so that things are a little bit more collaborative, instead of me going over these lectures, which I've already done once or twice, recorded. So you can also look at the recorded lectures from just last quarter. You can see the recorded lecture from the last quarter are a little bit more free-flowing. Depends on what people ask. We can talk about different parts of the lectures, or something new maybe come. You might talk about something a little bit outside what already covered in the lectures. So we'll try to do that again. So for example, the next time you can take a look at the first. So I'm going to go over most of the first lecture, more or less, at a let's say faster pace. So you can look at the first lecture if you feel things are a little bit too fast. The spring 2020, the first lecture, and then a little bit of lecture 2, and then I'm gonna hopefully assign what you should look at for the subsequent weeks. So any questions so far? Does this look like a plan? So one thing to mention is about attendance. So because of the way that we approach, so just it's like more of a discussion. What happened last quarter is that not many people showed up. That's my guess. It's going to happen this quarter as well. So what I'm doing is I'm not going to require you to attend, but the people that attend, and you can keep track using Zoom and otherwise, the people that attend and participate in class, just like logging in and just leaving, that's not going to cut it. If you participate regularly in the class, I'll try to take that into account. If you need a bump in the end, I'll try to take that into account. There's no like formal grade assigned to it, but I'll know you, and when it matters, I'll remember you, and hopefully it will have a positive impact on your grade. If you don't like find the lectures necessary, you'll see so most of this is easy. You can do it self-study and stuff like that, and you're going to do great in the homework and in the exams. And then feel free to not attend. That's fine. But I would generally expect that most of you would benefit from coming to class and participating. It's like an extended office hour. So you're because we're not in a hurry to cover the material. The material is already covered in the video lectures. You can always go there. We can spend more time, be a little bit slower in certain parts, especially the parts that you would have trouble. So I usually ask people at the start of every lecture, have you gone through the material, and which parts were like more problematic, difficult, or do you have any questions about specific parts? And we start from there usually, or I will give a brief recap, and then we'll go through this. And we might sort of play a game that, like, I ask someone to nominate someone to answer a question or something like that. Don't be afraid of just participating. It's good. Or you can say, I don't want to talk, like I don't want to answer. It's the next person, or you have difficulty, like you're in a place that you can't sort of communicate. You can sort of communicate via chat, or if you don't want, it's fine. But just be aware that we're trying to get you guys involved a little bit in the lectures. So now, is there any questions, comments? Material is fine, like these ideas are okay. You guys are really quiet. Any questions, comments?
So the textbook is required, or?
Oh, the textbook, good. It's hard to say. I'm not going to force you to buy it, but I'm going to assign homework problems. And sometimes I'll also like post the picture of the problems. But if you can somehow gain access to enough of the book to do the homework problems, then you'd be fine. It's a good book if you can somehow get your hands on it, or a version of it, or rent it, or I don't know. If you have a friend who can find an online version, or you have access to it, that would be great. I mean, it used to be provided during the COVID, I think in last spring, for free online, but I don't think it's available anymore. But that's the extent to which I require it. So we all have homework from it. But generally, it's a good book to learn from if you want to do self-study. It's one of the better books out there. I see a question. Between the materials and the class, which resource would be the most beneficial to study for the test? So that's a hard question to ask, but also to answer. But generally, the things that I emphasize in the lectures are important. And if you come to the lectures, you'd understand which parts I emphasize more, and those are the parts that that are going to have like a more prominent role in the tests and the exams. but you can also look at the slides. So I'm going to post the slides as well. There is a certain selection of topics that we go over, and that's mostly what.
Oh, hi, Professor. I have
Yeah.
a question about the grading. So, will you curve the grade, or you just give an A if we get 90% or above?
No, it's going to be like curved in that sense.
Okay, thanks.
No problem. Any other questions? Okay, so let me try stop sharing. I'm gonna, you still can ask questions while I'll bring up figure out where my slides are. So we're gonna start with the review of linear algebra. And let's see if I can clean this up where I have to. Sorry, I guess I have to, just give me a second. This is not, one. Okay, sorry, let me have a version of the slides which is not appropriate. So no questions. Let me try to figure out something which is a little bit better. Sorry, just give me a second. Okay, let's not worry about this. I'm gonna use these. I see a couple other questions in the chat. How much time are we given for the midterm and the final? More than enough, I would say. It's like a day or two. Do you suggest we preview materials before? Yes, that's what I was hoping, that you would watch recorded lectures before class. So the last time people complained, and that was I would say legitimate complaint, that would be a little bit too much work. So the more you can do it, the better. But I'll try to help you guys figure out which part to look at. But generally, look ahead a little bit. The things that we discussed, look a little bit further than that in the lectures. That's the idea. Okay, any other questions in the chat? Or so I'm going to use these slides. These are not the best version, but they're clean. So we start with the review of linear algebra. So this is the entire table of contents. But so I'm hoping that you guys know linear algebra. But from my past experience with people in the classes, that most of you either have forgotten or have not seen all of the topics that we need. So first, I would encourage you to go and refresh your memory about linear algebra. And I'm going to go over this a quick review. And some parts might be new to people, actually. So it's like a review slash teaching linear algebra. But I can't do a very thorough job of teaching it because we don't have time, and this is not a linear algebra course. So these are the main topics that we care about. So The first few hopefully are familiar to people. Towards the end of this list, there are topics that my guess is that some or most of you have not seen, sorry. So we're going to start from the basic ones and we move forward. Okay, so the basic idea is, so I'm going to skip this. This is like the recap. At the end, you have to hopefully understand what this slide is about. That's like a very short summary or bird's eye view of the things that I'm going to do in the linear algebra. So I'm going to skip this. The first thing that I want to discuss is, so you guys still can hear me, right? And see the slides, right?
Yeah.
Yeah, okay, good. So what we do is we start with linear independence or linear dependence. That's the first concept that we start with in linear algebra. And let me ask you guys, anyone, the definition is there, but I want to know if anyone can tell us about this. What is linear independence or linear dependence in linear algebra? Anyone remembers the concept? Sorry, let's see. I have to. I see something in the chat. Let's see. Oh, no. Okay, nothing. No one wants to tell us about the linear independence. Okay, so let me just remind you. That's fine. If you have a set of vectors, x1 up to xn, they're called linearly independent if this formal statement holds. If you can find a linear combination of them that's 0, then the coefficients have to all be 0. So let me write it more formally. So let's say x1, that's a little strange. Okay, so x1 and x2 are linearly independent if whenever I have c1 x1 plus c2 x2 equals 0, then c1 is equal to c2 is equal to 0. In other words, I can't have a linear combination. This is called a linear combination. C1 and C2 are numbers. X1 and X2 are vectors. I can't have a linear combination that's 0 with non-zero coefficients. So if any linear combination is 0, then the coefficients have to be 0. And this is the general statement. So if you have a collection of n vectors, then if you set this is a general linear combination of them with coefficients ci's to 0, if it turns out that this is the case, then the coefficients have to be 0, all of them. And if it turns out that you can get some linear combination, it's to be equal to 0 with some coefficients being non-zero, then you'll say that the set is linearly dependent. So the way I'm stating it here is the linear dependence. So there exists some coefficients, not all of which are 0, such that this linear combination is 0. So the easiest case where you have linearly dependent vectors is, let's say, if I have x1 and then the next one is like 2x1 or a multiple of x1, then I can write x1 minus 2x1. That's like x2 equal to 0. And so I have coefficients like 1 and -1, and the linear combination is 0, so they're not going to be linearly independent. So I can do it with any multiple here. It could be like -5 or something like that. So any two vectors, one of which is a scalar multiple of the other, they can't be linearly independent. Okay. Does this ring a bell? People remember this concept? Anyone? Say how many people I can like raise your hands if you have seen and now remember linear independence. Okay, no one wants to raise their hand. Okay, you guys are really shy or really don't remember. Okay, so how about, okay, so 1, okay, Hortensia, brave, okay, brave few souls, okay, so 2. So let me, at least 2 people know. So let me ask you this question. So which one of these 2 sets of vectors are linearly independent? So we have 2 sets of vectors here. Given this definition, which one do you think is a linearly independent set of vectors?
The one on the right.
Right, this one. Why?
There's like no scalar multiple that like makes the vectors equal to each other.
Right, so for 3 vectors, it's a little bit more complicated because none of which could be like the scalar multiple of each other, but there's still, it could be like a set of coefficients that I could cook up that makes this, make them linearly, or make the linear combination 0. So the way to prove it, this is linearly independent. The way to prove it is set it equal to 0 with unidentified coefficients, and then try to prove that these coefficients have to be 0. Once you do this, you'd get 3 equations, right? So the first equation would be like C1 plus C2 plus C3 is equal to 0. So if you remember how to multiply scalars and add vectors, that's the first equation. There's a second equation, and there's a third equation, which is like C1 times 0, C2 times 0, and C3 times minus 1. So you get minus C3 is equal to 0. So this just shows that C3 has to be 0. Once you have that, then you plug it back into the 2 equations, so you can drop the C0, and then from the 2 equations you can solve for C1 and C2, and that those turn out to be 0. So that's the formal way. You can also see that like the basic check that one of them is a multiple of the other, that is not true, but that's not enough necessarily. Now, how about this one? Is this a linearly dependent or independent?
This is dependent.
Yeah, why?
Because the first vector, the first vector is what's that called? If you times 2, you get the third vector.
Okay, 2 times this is equal to the second vector, yes. And so whenever a subset of a set of vectors is linearly dependent, then it can't be linearly. So this is the subset, this simple 2-member subset is linearly dependent because one of the vectors is the, sorry, not the second one, right? So these 2, this and this.
Yeah.
So yeah, so the first and the second are linearly independent, but the first and the third, this set is linearly dependent, and because it's a subset of the bigger set, that bigger set has to be linearly dependent, because I can add like 1 here, -1 here, and 0 here as coefficients, and then sorry, negative, for example, 2 here, 2, 0, and -1. 2, 0, and -1, and then the sum would be 0. Okay, something like that. So there's a non-trivial set of coefficients. Does this sound good to everyone?
Yeah.
Okay. No questions, comments? Okay, so what else do we have here? There is a bit of a little exercise that if you have a set of non-zero pairwise orthogonal vectors, I'll talk about what orthogonality means, but when we get there, just go back to this exercise and try to do it. If the vectors are pairwise orthogonal, for example, these 2 vectors are pairwise. These are orthogonal. Pairwise orthogonal means every pair, if you pick any two, and they're going to be orthogonal. That's not the case here, nor is it the case for this. But if it happens that the vectors are pairwise orthogonal and none of them is 0, then they're linearly independent. It's a very useful fact. And any set of vectors that contains the 0 vector cannot be linearly independent. So they have to be linearly dependent. You can also verify from the definition. Okay, do them as exercises. So the next thing to recall is this span, which is the set of vectors that can be written as linear combinations of a given set of vectors. So I have x1 up to xn, and I look at all general linear combinations of them, where these coefficients are free to vary. And as I vary these coefficients, I get different vectors. And if I look at the class of all those vectors, that's a set, and that set is called the span of x1 up to xn. So here's a quick example. So you have these two vectors, if you write down the definition of a span, it's the set of all vectors that can be written like this for T1 and T2 in R. I can sort of rearrange a little bit. T2 times 2, and I mean, you can just verify that if I multiply these, this is the same as this, because one of them is twice the other. Basically, this whole vector would be in the direction of this vector, and the factor would be this. And then if you think a little bit, as I vary T1 and T2, this would vary in R. So this can be any number. So this set is the same as this set. So this simplifies to this. And so we have a representation of the span as the set of all vectors that are a scalar multiple of this vector. So the span of these two vectors then can be described as this. So can we picture this geometrically? What is this set? Anyone knows what this set is? Let's say if I have the three-dimensional vector space x, y, z, what would this set of vectors look like?
The xy plane.
Okay, great. You just gave the final answer. So let's say the two vectors are, this is one vector, and the other one is this vector. So this is 1, 1, and this is 2, 2. Okay, so you can see the two vectors are in the same direction. And then the set of all linear combinations of them would be, oh, actually, it's not correct. So you said xy plane, it's not xy plane, sorry.
I mean like the line, yeah,
right,
so
okay.
yeah.
Okay, yeah, that's the answer to a different, another question that will come up. But yeah, so this is going to be the line in the xy plane. So it's the line that's in the direction. I haven't written, I haven't drawn it nicely so that you can see, but it doesn't go outside the plane. So this is the line that's inside the xy plane. Okay, if you imagine the plane here, everything is in the xy plane, and there's this line there which goes through 1 and 1. The entire line, that's the span. Okay. Okay, so the span of these two vectors is like that. If you have two other vectors, let's say here we have these two vectors, which is one of them is 1, 1, 0. The other one is the second coordinate, which is y, is negative. So it's -1 here. So that's the second vector. So these two vectors, if you go through the span calculation, you can simplify and you get something like this. And this can be written as a general vector alpha beta. So as T1 and T2 vary in R2, these two coefficients can take any values. You have to reason for yourself a little bit, but basically they're free to be any values. the reason to see this is that if I set this equal to alpha, t1 minus t2 equal to beta, this system of equations can always be solved for any alpha and beta. So I can always pick t1 and t2 to get any alpha beta here. So that's the this set simplifies to this, and I can rearrange this as alpha times this plus beta times that, and this is the definition of the span of 1, 0, 0, 0, 1, 0. And so this calculation tells us that the span of these two vectors is the same as the span of the standard bases. And both of these are just the xy plane. That's the answer to this one, which is a two-dimensional space. This is a one-dimensional space. I'm going to get to the dimension. But you can see that's the span. So these two vectors are not, they're linearly dependent. And you can see the span turns out to be a line, which is one-dimensional. These two vectors are linearly independent, and the span turns out to have the dimension, which is equal to the number of the vectors there. And this is no coincidence. But this is the concept of span. Okay, so the set of all vectors that are spanned by these two vectors are the set of all vectors that can be written as the linear combination of the two. And the idea is that anything in the plane can be written as a linear combination of these two red vectors. And exactly the same set of vectors can be written as the linear combination of these two green ones, which are the standard bases. So the span of these two sets of vectors is the same. Okay, questions, comments? All good. Sorry, I made a mistake here. I'm trying to figure out my Zoom. This is really funny. Okay, sorry. I have it open on my computer. Okay, never mind this. So no questions so far? Sorry, let me figure out. Okay, I can't get this. Okay. Okay, so no questions? Comments, nothing? Okay, so this like the discussion sort of naturally goes to this concept of bases and dimension. So a set of linearly independent vectors that span a subspace V is called the basis for the subspace. So here we have, think of this green, the xy plane, as a subspace. I'll come back to the subspace. Let's say a set here, and we know that this is a linearly independent set of vectors, and we know that they span that set or that subspace. So this set of vectors is a basis for that subspace. Similarly, this set of vectors is linear independent, and they span the same object, and so this set is also a basis for that. So this basically the xy plane, I can write it as this. That's the V here, and it can be written as the span of these two different sets of linearly independent vectors. That's just the previous example, and it turns out that all the bases, so you can have different bases for the same subspace. So you could have different, basically, sets of linear independent vectors that span the same subspace, as you can see here. But it turns out that the number of vectors in a basis for a subspace is fixed. And that same number is called the dimension. Okay, so you can see this is a basis, and this is also a basis. They can't have different number of vectors in them if they're the basis for the same subspace. And that common number is called the dimension of V. So the dimension of the xy plane is 2, which is what you intuitively guess, or that matches your intuition or intuitive notion of dimension. And we write it as dimension of V equal to 2. So this notion of dimension sort of formalizes the idea of degrees of freedom. So that's one way mathematicians formalize the degrees of freedom. So you have 2 degrees of freedom. You can see here, alpha and beta are free. There's no relation between alpha and beta on this plane. I can choose them whichever I want. Whereas, for example, the 2 coordinates of a vector in this subspace on the line are not free. If I choose one, the other one has to be the same as the first one. So there's only 1 degree of freedom. And so you can see, for example, this is not a basis for the line. Okay. Whereas, so can anyone tell me why this is not a basis for the line based on the discussion?
They're not linearly independent.
They're not linearly independent. Okay, so what is a basis then? Can you give me a basis?
Just like a random example.
A random
Space is the
example.
vector that spans the space. Like
It's
for this case, a vector that spans this line.
Yeah, in general, it's a set of vectors that span, and the set has to be linearly independent. In this case, a single vector can do. So what would it be?
1, 1, 0.
1, 1, 0 would do, yeah. So I can write the V, if this is V, call this V, then V can be written as the span of this. A single non-zero vector is always linearly independent. You can go from the definition. And the span is just exactly this. So the span is a set of all linear combinations. A linear combination is just the scalar multiple of it because there's no other thing to combine with. And so that's the span of this. So this is a basis. So this, if you want to be formal, the singleton set that contains this vector is the basis. So this is a basis for V. Can you give me another basis for this? A different basis?
Another basis for this line?
Yes.
2, 2, 0.
Yeah, 2, 2, 0, that's another basis. Like -1, -1, 0, that's another one. There are many. Anything on this line, any vector on this line, if you look at it as a singleton set, that would be a basis. But this can't be a basis, right? It violates one of the conditions. So everyone understands the notion of, and you can see all of them have the same number of elements. All of them have a single element. So linear independence, span, basis, dimension. These are the key concepts. Everyone happy with this? Questions, comments? Okay. Let's see. So the next set of topics is related to a matrix, and so we start with some. So before doing that, let me just point out what a subspace is. So anyone knows what a definition? So I use this term subspace, and this has a specific meaning in linear algebra. Anyone knows or recalls what a subspace is? Definition of a subspace. So V is any subset of, let's say V is a subset of RD, is a subspace, is a, let's say, linear. When we say subspace, usually we mean linear subspace a linear subspace if, or of RD, let's say, if what happens? What is this special property?
Is it just that all the vectors in the subspace belong to the bigger space of which this is a subspace?
That would be the definition of a set. So you could say V is a subset, right, of RD if all the elements in V belong to the bigger set, which is RD. So subspace is a little bit more special, has more properties. Linear subspace.
I think sorry, go ahead.
Oh,
Yeah.
I was just gonna say, is it like the axioms of like closed under addition, multiplication? I don't remember.
Yeah, great. So it's just it's simpler. So to just it's not the axioms of linear algebra, but it's just the two properties. So if two vectors x and y, I'm gonna like put a bar on their things to emphasize that they're vectors. So if x and y are vectors, and x and y belong to V, then their addition belongs to V. And if I have like a scalar alpha in R and x in RD, and I know that x is in V, then alpha x is in V. Okay, so if I multiply some vector by a scalar, it would be in V. If I add two vectors that are in V, the result would be in V. This is equivalent to just saying that if, let's say, x1 up to xn are in V, then any linear combination would be in V for any C1, C2, Cn in R. So just the simple thing to remember, a linear subspace. V is a subset of RD, which is closed under taking linear combinations of its elements. So closed means this. So if this property holds, they're saying they say that V is closed under addition. If this property holds, they say V is closed under scalar multiplication, meaning that you start from vectors in V and you perform this operation. The result of the operation does not leave the space. That's the meaning of being closed under something. And so if you generalize basically these 1 and 2, it just the result is this, that something is subspace, a set of vectors is subspace if you take any linear combination of the elements in the subspace, and that linear set of combination, the linear combination of those vectors is in V. You can clearly see here, we did it with two vectors, but you could have like multiple vectors. So the plane, xy plane, is a linear subspace because if I take any set of vectors, if I add them up, and I can take this and rescale everyone like by a bit, and then add them up, things wouldn't leave the plane. You can't magically gain any component in this direction that moves you outside. So everything in the xy plane, if you add them up, they're going to remain in the xy plane. So that's why this is a subspace. Similarly here, so if I take two vectors here, add them up, I'm not going to leave the line. I can't get a component just pushing me outside this space. So the line is a linear subspace. And you can verify easily that a span of any set of vectors is a linear subspace. So that's the source of getting linear subspaces. So whenever you form a span of a set of vectors, it's a linear subspace with this definition, in the sense that it's going to be closed under linear combinations, basically by definition, more or less. There's a bit more argument because if you want to formally prove it, you have to take elements from the span, which themselves are linear combinations, and then form the linear combinations of those. But then you multiply everything out, the result is still a linear combination of the original elements. So I encourage you to try to prove this statement, that the linear span, or the span of any set of vectors, sometimes this is called the linear span. But usually we don't emphasize. I'll say subspace, I mean linear subspace. I say a span, I mean linear span. So the linear span of a set of vectors is a linear subspace. Try to prove this using this. So to prove as an exercise. Okay, so that's the subspace. Any questions? Yeah, so this was not clear. So into the spring 2020 lectures and last quarter, someone asked, it's a great question. And it's just the basic building block of linear algebra. These subspaces are the building blocks. And so next we talk about the column space, which is a particular subspace. It's one of these guys, one of these type of objects that's closed under linear combinations. And this subspace is associated with a matrix. So the short definition is that the column space of a matrix X is the span of the columns of X. So if you understand the span, it's just nothing but the span of the columns. So to be more precise, let's say I have a set of vectors x1 up to xp. These are in Rn. So this is a subset of Rn. Each vector is in Rn. These are n-dimensional vectors, so they have n coordinates. And then say I form a matrix by putting them as columns of this matrix. So that's the notation that I'm sometimes using, that these bars mean that I concatenate them horizontally. So I put them side by side. So each one is n-dimensional. So the dimension here is n, and then I have p of them, so I get n times p. So that matrix is n by p, and each of the columns is one of these vectors. So the span of, so the column space of X is just the span by definition, span of X1 up to Xn. This also has another name, which I usually use. It's called the image of X. It's another name. It has other names as well, but your book sometimes uses L of X for this. But I'm going to stick with this for a reason. But that's the definition. But there is a nice way of representing the span of a matrix, and that goes back to the idea of how you multiply a matrix by a vector, or a vector by a matrix. So the idea is, how many people remember matrix vector multiplications? So let's say I have a matrix n by p, and then I have a vector p by 1. Can I multiply the two? And how would I do that? Say this is X, and I have a beta matrix, a beta vector. So beta is like beta 1 to beta p. How do I multiply the two?
So
is
it's
it
like
valid?
the first item.
Go ahead.
So it's like the first item in the first row in the first matrix times beta 1 plus the second item times beta 2. Add all of them up to beta n.
Beta p, yeah. So x1
Oh, beta
p,
p.
beta p, yeah. So right. So that would be the what? This would be
The first first row.
That would be the first row, which in this case would be the first element. First, you figure out the dimensions, right? So what is the dimension of the product?
It's n row with one column.
Right, n by 1. So the inner dimensions have to match. and then you collapse, basically this part collapses, you get n times 1. Sorry. So, okay, so the, and then what basically happens, what I think Albert described, is the first row gets multiplied point-wise or coordinate-wise by beta, and then you sum the entries. So that's what happens here. And then you do the second row, let's say, multiplied by the same thing. So you get x21 beta 1 plus x22 beta 2 plus x2p beta p, and that gives you the second line or the second entry, and so on, right, until you get to the last. So this is the like probably the common way that you learn how to do the matrix multiplication. So you do row-wise calculation. One row gets multiplied by, or in general, if you have two vectors, two matrices, you go, the first row gets multiplied by the first column. The first row gets multiplied by the second column, gets you the 1, 2 element. The first row gets multiplied by the third column, the 1, 3 element, and so on. And then you go to the second row, and so on. There is another way of viewing it, which is what we usually view in this course, or it's really good to remember, is viewing things column-wise. So what happens if I want to operate along the columns of this instead of the rows? The thing that happens is that you can show that exactly the same result follows if you do this operation, that instead of doing the row-wise calculation, you just take the beta 1 times this entire vector, and then beta 2 times this entire vector, and beta p times this entire vector, and then add them up. So you get the linear combination of these vectors, and that would be exactly the same as this. So this is basically just beta 1 x1, but this is like one of them is a scalar, the other is a vector, right? Dot 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 beta p xp, and that would be exactly the same vector that you'd get using your usual way of multiplying things. But this is very useful to remember. Okay, so if you multiply from the left, or whatever this side is, I can, depending on who's left or right you're talking about. But if you multiply from this side, a vector, the effect, you multiply a vector on this side, or a matrix by a vector on this way, then the effect is that you're going to take a linear combination of the columns of X with coefficients that are the elements of beta. That's what matrix vector multiplication would do. So if you understand this, I would encourage you to verify this for yourself, that this is indeed the case. Then this gives us a very nice compact way of writing a linear combination. So this is a general linear combination of these vectors. I can just write it compactly as x beta. Okay, and so the span of these can be written as summation beta, or let's say I can write it as beta 1 x1 up to the vectors that look like this, beta p xp, where beta 1 up to beta p are generic numbers. So that's the way to write the span. So before we had c's here, so these were c's, but these are dummy variables, so you can name them anything you want. You're naming it beta in anticipation of regression, but that nicely can be written as compactly as just x beta, where now beta is a vector in R to the p. So as I vary x in R to the p, I form x beta, and this gives me the general formula for elements of the span. Okay, so this is a general linear combination of the columns of X. Okay, so this is nothing new except that we are using matrix vector multiplication to do a compact, or to get a compact representation of the span of the columns. And so the column space of X can be compactly written as this. So this is the set of all vectors that can be written as X beta for some vector beta. Okay. Is this clear? Questions, comments? All good?
Yes.
Okay, yes. So this is also called, as I mentioned, image or the range. You can verify, because it's a span, and I mentioned a span is always a linear subspace, it should be a linear subspace of Rn. It's a linear subspace of Rn because the vectors are in Rn. So the span of this would be vectors that look like this, and all of these vectors are in Rn. So the P is the number that we have, but the dimension of each vector is n dimensional. So this is a subspace of Rn. So the image of, if I have a matrix n by p, which I write like this, then the dimension, the image of X would be a subset or subspace of Rn. The dimension of the image, so it's a subspace, and any subspace has a dimension. The dimension of the image is called the rank of the matrix. Okay, so that's what the rank is. It's very important in linear algebra. It's just the dimension of the image, and the image is just a subspace. So as long as you understand what the dimension of a subspace is, then you would understand what the rank is. So another way of stating the dimension, so here, go back to this. So we define the dimension as the common number of any bases for a subspace. Another equivalent statement is dimension of V. Anyone can give me an equivalent statement without referring to the bases. So what is another way of stating what the dimension is? But if you recall, well, how did you learn about the rank of a matrix? What is the rank of a matrix? I said that it's the dimension of the image of X, or the column span of X. But how did you learn about the rank?
Dimension of column.
Column space. Okay, so that's the thing that I mentioned. But there's another way of saying it. I was hoping that someone has learned it that way. Is there any other alternative way of saying what the rank of or the column, this is called the column rank sometimes. What is the column rank or the rank of X? The column rank of X. Or alternative statement about the dimension. It's a common number, or the number of elements of any basis, or the maximal number of linearly independent of a set of linearly independent vectors from V. It's the maximum or the maximal, the largest. This is a funny way of saying the largest. The largest number of a set of linear independent vectors. The number, the statement is not correct. So the number of elements, the maximal number of elements of a set of linear independent vectors. So you can form subsets of V, and some of which would be linearly independent, some of which would be linearly dependent. And among all the ones that are linearly independent, all the possible subsets of V that you can make that are linearly independent, there is a maximum number of elements that you can allow. beyond which you can't, and that maximal number is called the dimension. So for example, here, that maximal number is 2. Any set of three vectors that you take in the plane would be linearly dependent. You can't go beyond 2. Otherwise, because if you can take 3 elements and they're going to span the plane, and then they would form a basis, but any basis would have at most, or exactly 2. So so the number of elements of a basis would put an upper bound on how many linear independent vectors you can form. So here you can have sets of 0 or 1 or 2 linear independent vectors, but you can't have sets of 3 linear independent vectors. So that's another way of saying the dimension. And so the rank, this is also called, called the column rank, in fact. But you learn that the column rank and the row rank. So you can define the row space similar to column space. It's the set of all linear combinations of the rows, or the span of the rows. And then the row rank would be the dimension of the row space. But then a resulting linear algebra tells you that these two numbers, the dimension of the row space and the dimension of the column space, are the same. So there is a unique rank. There's just one rank. So you can just drop this. But the way we define it is the column rank turns out to be just a rank. And so you can say that this is the maximum or maximal number of linear independent columns of X. That's the alternative way of saying it. So you look at the columns of X. If they're all linear independent, great. That's the maximum possible, and that would be the rank. But sometimes they're not all linearly independent, so you have to drop some of them. And you drop one, let's say they become linearly independent, great. Otherwise, you have to drop at least 2, and so on. You drop as much as possible, like as little as possible, to get a linear independent set, and that would be the number of elements that remain is the rank. So, for example, if I have a matrix which is 1, 1, 0, 2, negative 2, 0, 2, 2, 0. If I put these vectors as columns of a matrix, so what would the rank of this matrix? If I have X, the question would be, what is the rank of X? If you understand those ideas. Can the rank be 3?
The rank is 2.
Why?
Because the first and the third one is basically the same. It has 2 linear independent vectors.
Right, so first, the rank can't be 3 because if I look at the set of all the 3 of them, we have established that they're linearly dependent. So, so I have to drop 1. For example, I can drop this one, but then I still have the remaining one are linearly dependent, so that's not a good choice. But how about I drop one of these that are, so I drop this. I just take, for example, these 2. Okay, so the set 2, negative 2, 0, and 2, 2, 0. That is a subset of the columns that's linearly independent, and that would be the maximal number possible because I can't have 3, but I can have 2 now. So 2 would be a rank. Okay, so 2 is the maximal number of linear independent columns. It doesn't mean that any set of 2 vectors from the columns that you take is linear independent. I can take these 2, which is not going to be linearly independent. But I can at least have one subset of 2 elements from the columns of X that's linearly independent. So linearly independent, hence rank of X is 2. Okay. How about the rank of this matrix? If I form the matrix X, which is 1, 1, 0, 1, minus 1, 0, 1, minus 1, minus 1. Put these in the columns. Anyone?
The rank is 3, right?
Yes. Why?
Because they're independent.
They're linearly independent, and the maximal number of linearly independent columns is 3. I can't have more than 3 columns because they're just 3. And so whenever you have linearly independent columns, all of them are together are linearly independent, then the rank would be just the number of columns. That's like the typical, the good case. The matrices that have, so this is the maximum that the rank can be 3, right? Or the column rank. And because I said that the rank from the row and the column is the same, the rank can be at most the minimum of the number of rows and columns. I'll come back maybe to this later, but in this case, the number of rows and columns is the same, so the rank can be at most 3. And this has the maximal rank. So a matrix such as the rank is the maximum possible is called full rank. So X is full rank. So this was a little bit fast, but take a look at the definition of full rank in Wikipedia, or go through it in the lectures or videos. And this is going to be key for us. So what it means for a matrix to be full rank. The full rank means the matrix, the rank is the most possible. In this case, the most possible is 3. The rank can't be more than 3 for a 3 by 3 matrix, and it's the most possible. This is not full rank because the rank is 2. It could be 3 because we have 3 columns and 3 rows, but a rank is less than that. So this is sometimes called rank deficient. Okay, I think that's good for now. So I'm going to stop here. It's a good place to stop. I would encourage you to think about the rank and the idea of full rank and so on, and go over the rest of these so the null space or the kernel, the idea of inner product and orthogonality, orthogonal complement, and norm and distance and projection, at least this far. And if you get a chance, like, go over the spectral decomposition as well. That's the entire and positive semi-definite matrices. So let me go back to the first slide. So we covered these and most of this, but there's the kernel of X that remains. Just go over this from the slides and try to go over these concepts from the lectures, the previous lectures as well. If you really get a chance to go through these two, the discussion is quick, and we're not going to spend too much time on this, but this is key. So this third point, especially the idea of projection. So try to go over them from the recorded lectures, and hopefully come back later. On next lecture, we talk about these. Okay, sounds good. Questions,
Professor?
comments? Yeah.
I'm gonna post the slides.
Yes, I'm gonna post them on the box folder.
Okay.
Yeah, and the
Okay,
lecture videos. Yeah, no problem.
Okay.
Any other questions?